Welcome. Okay, we're going to look at linear transformations. A map or mapping or function is an unambiguous rule for sending the elements of the non-empty set X to the elements of the non-empty set Y, denoted F maps X to Y. So let's put or function. Also see definition 1. Example 11.1. Let f map the integers to the real numbers be given by f of x is x squared. This is a map or function that sends an integer to its square. Okay, for example, f of minus 5 is 25. F of 2 is 4, and so on. And so here you would say the image of the map F is the set of all elements that come out of this. So we've got 0, 1, 4, 9, 16, 25, and so on. The domain of the map F is X by definition of domain, and the codomain of F is Y, or you could call that the target set. But it doesn't mean that the set Y or the codomain is equal to the image, because in this case, have a look, the image is a subset of the real numbers. But it's not necessarily equal to that set on the right. In example 11.1 above, the domain of F is the set of integers. The codomain is the real numbers, and the image of the map, denoted F square brackets X, here it's F of integers. It's the set of all elements of the real numbers that are of the form f of x. So here f of x is the set of all squares of integers. And so that's just what we've written up there. So in another context, z superscript 2 might be used to refer to the Cartesian product. We don't mean that in this case. So this is the set of all pairs a comma b such that a and b are integers. Sometimes people use z superscript 2 to refer to this set, but I don't mean that here. Definition 30. Let f map x to y. The preimage of a preimage is a subset w, that should say is a subset w of y. F superscript minus 1 of w is the set of all elements x of the domain such that f of x belongs to w. Define a map f sending real numbers to real numbers by f of x is x squared. Find the image of f of r, and find the preimage of 1, 2, 3. Okay, so f of r, this is the image of f. And so this is the set of all real numbers x such that well, actually, let's say the set of all real numbers y is such that there exists a real number x satisfying f of x is equal to y. So the set of all squares of real numbers this is all the real numbers that are greater or equal to 0. And there's another way to write this. We could use a superscript to denote this. So R superscript, and then I'll just put a greater or equal to sign in the superscript or in round brackets, referring to the set of all real numbers that are greater or equal to 0. Now in interval notation, it looks like this. Okay, so that's the image of the map. Now the pre-image of the set 1, 2, 3 this is the set of all elements that map to 1, 2, and 3. So taking square roots of each of those elements, we've got 1, minus 1, root 2, minus root 2, root 3, and minus root 3. All of these map to 1 or 2 or 3. Okay, let's move on to the next page. All right, first thing, we'll change that x to a t. So let V equal to R t be the vector space of all polynomials with real coefficients. So that's what that says there. Polynomials with real coefficients. Define the map D from V to V by D of the polynomial P of t is the first derivative with respect to t. This is an example of a map. Now consider the pre-image of some polynomial Q of t. First, let's take a look at what this map does. So D of, say, t squared plus 5t minus 7, for example, this differentiates, and so we get 2t plus 5. Now this is a polynomial with real coefficients, and so the result is in V. So it does map a polynomial to a polynomial with real coefficients. Okay, let's have a look at the pre-image of something. So D inverse of, say, let's just choose a set of polynomials, 3t squared minus 12t plus 8, and then let's choose another one, 5t cubed minus 2t plus 6, for example. So what's the pre-image of this? Well, we've got to find out where each of these polynomials came from on the other side of the map. So since the map says differentiate, going the other way is integrating. So we integrate these. With respect to t. Okay, and there are multiple possibilities for these because there's the constant of integration in there, right? So each of these has infinitely many antiderivatives. Okay, example 11.4. Let V equal R of x be the vector space of polynomials with real coefficients. Again, let's change this to a t, because the rest of it talks about it with respect to t. Define a map f from V to R by f of the polynomial p of t is the definite integral between 0 and 1 of p of t. Okay, so that's an example of a map. You end up with a real number Definition 31. A map F sending x to y is said to be a linear map if both x and y are vector spaces over a field K, and for all vectors u and v in the domain X, f of u plus v is f of u plus f of v. So we can say F is a vector space homomorphism when this property holds. Third property. For all scalars k and vectors u in X, f of k times u is k times f of u. So if these properties hold, then you have a linear map. It's also called a linear transformation. So clearly, if f is a linear map, then f of 0 times v is equal to the 0 vector. Example 11.5. Let f map 3 space to 3 space by f of x, y, z is x, y, 0, where we understand R3 to be the vector space R3. This map F projects the vector x, y, z onto the x, y plane. F is a linear map. Okay, so let's draw a little picture. So we have a point here, and so from the origin to the point, we've got an arrow representing our vector. So what's happening is it's projected straight down, and you get a vector in the xy plane. Okay, let's show that this is a linear map. So let's look at the properties. So these are both vector spaces. So number 1, R3 is a vector space over the real numbers. Okay, second property. Let's take two vectors. I'll write them vertically here. So x1, y1, z1 plus x2, y2, z2 equals f of, so now I'm just going to add those two vectors, x1 plus x2, y1 plus y2, z1 plus z2, and then the rule says we just replace the third coordinate with 0. Okay, so we've now applied the map. So let's check whether this is the same as f of x1, y2, z1, sorry, x1, y1, z1 plus f of x2, y2, z2. Okay, so we have x1, y1, 0 plus x2, y2, 0, which is x1 plus x2, y1 plus y2, 0. And it's the same as what we have here in the line above it. So the second property holds. Okay, now let's have a look at the third property. F of k times x, y, z is equal to f of kx, ky, kz, which is kx, ky, 0. And we can factor the k out of this, and we see that it's k times f of x, y, z. Okay, so the third property holds. So we see that the map F is a linear map. All right, let's move on to the next page. Example 11.6. Let G map 2 space to 2 space by G of xy is x plus 1 comma y plus 2, where we understand R2 to be the vector space R2. Determine whether G is a linear map. Well, it won't be a linear map even though these are linear functions, and the problem is the additive property will be a problem with the plus 1 and the plus 2 here. So let's see why. So let x1, y1, and x2, y2 be in 2 space. So then G of the sum is, and I'll write this vertically as well. We have G of x1 plus x2, y1 plus y2. And so this rule says take the x coordinate, add 1 to it. So x1 plus x2 plus 1. Take the y coordinate and add 2 to that. Okay, so there we have this. Now let's have a look at G of x1, y1 plus G of x2, y2. So that is x1 plus 1, y1 plus 2, plus x2 plus 1, y2 plus 2. Then we add these two together and we get x1 plus x2 plus 2, y1 plus y2 plus 4, and this is not equal to the line above. Okay, so what we've learned then is that G is not a linear map. Because G is not an additive homomorphism. Doesn't satisfy the second property. Example 11.7, let V be R of T. So this is the space of polynomials in the letter T with real coefficients. The derivative is a linear map. Okay, so let's see why. So first note that R T is a vector space over the real numbers. Now let's have a look at the additive property. So let P of T be equal to, say, A0 plus A1 T, and so on up to an t to the power of n. And let's let Q of T be B0 plus B1 T, and so on. up to be m t to the m. Okay, I'm not assuming that these have the same degree here. Okay, now let's assume, without any loss of generality, that n is greater or equal to m. Then we can pad out q. So we can pad q with zeros in the coefficients. So both stop at t to the power of n. All right, and so I'll even say like this, where Bn can be 0. Okay, so given that setup, then what are we doing here? We're checking that it satisfies the second condition of a linear map. So d of p of t plus q of t is equal to, now you just sub these two in, you take their sum and then you differentiate. We have a0 plus b0, a1 plus b1 times t, and so on, up to an plus bn t to the power of n. Okay, then we apply the map, which is to differentiate. And so we get a1 plus b1 plus 2 times a2 plus b2 times t, and so on, up to n times an plus bn t to the n minus 1. Okay, and then you've got to show that it's the same as if you had differentiated those separately and then added them together. Okay, so, and that's easy to show. And then finally, the third property would say d of k times p of t is equal to k times d of p of t. And that's true because it's a property of differentiation, that the derivative of a constant times a polynomial is the constant times the derivative of the polynomial. So we can see that this is an example of a linear map. Okay, Theorem 36. Let A be an m by n matrix with entries in the field K. Let x and y be vector spaces of dimension n and m respectively. Define a map f subscript a, mapping the set x to the set y by fa of x is a times x. Then matrix multiplication f subscript a is a linear map. So let's see why. And notice up here in example 11.6, this is not expressible in terms of matrix multiplication because we have constant terms in it. Okay, so f subscript a of x1 plus x2, that should say x2, so change that, is a times x1 plus x2. Now we can expand this and say it's ax1 plus ax2. ax1 is f subscript a of x1, and ax2 is a f subscript a of x2. And so it has that first additive property of a linear map. Okay, second one, for all scalars k in the field of scalars and vectors x in the vector space x, fa k times x is a times the vector kx. Now, since that's scalar multiplication, we can move that through and put it on the other side of the matrix A. So we have k times a times x. Now ax is f subscript a of x, so this is k f subscript a of x. So when you can express your function as matrix multiplication, then it's a linear map. Okay, let's move on to change of basis theorem. Theorem 37, let x and y be vector spaces over the field K of dimension n over K. So let's say over the base field. So here we don't know what the base field is. For example, if this were R2, then the base field would be R. Let x1, x2, dot, 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 xn, and y1, y2, dot, 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 yn be respective bases of x and y. Then there exists a unique linear mapping f subscript a sending x to y satisfying fa x1 is y1, fa x2 is y2, and so on, fa xn is yn. There exists an n by n matrix A such that f subscript a of x is a times x, and applying each of these, noting that it's a times x, we have a times the concatenation of all those vectors is equal to the concatenation of all the vectors y. All right, let's see why. So A would be a change of basis matrix. Okay, so what we're going to show is that we show that we must have a vector space isomorphism. So we have a linear map such that the kernel of that linear map is trivial. All right, but let's look at the details. First, we'll show that it's a linear map. So first, f of x1 plus x2 is equal to f(x1) plus f x2, and also f of k times the vector x is k times f of x. Okay, now since x1, x2, etc. up to xn is a basis for x, all of the y j, all of these vectors, the yj, can be expressed as a linear combination of the basis elements x1 through xn. And so how can we say that? Well, y1 is a linear combination of those. So there exists an alpha 1 1, alpha 1 2, and so on, alpha 1 n, so y1 is a linear combination of the vectors x1 through xn. Likewise, y2 is a linear combination of those. So there exists alpha 2 1, alpha 2 2, and so on up to alpha 2n. Okay, and similarly for all the others, to alpha nn. Okay, so we can write this because x is a basis. All right, and so now we can write this in matrix form. A times x1, x2 up to xn, where A is equal to alpha ij. So just all of the numbers in here. Okay, and so also there exists a matrix B such that we can do this the other way around. Okay, and so what we're going to get then by substitution is that y1, y2, dot, 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 yn equals, now I'm just going to substitute this for this. So we have A times B, y1, y2, etc. to yn. And similarly, again via substitution, we have this. And so if this is the case, we must have BA is the identity matrix and AB is the identity matrix. So in other words, A and B are inverses of one another. And so that says that the linear map can be reversed, and it changes the basis. Okay, let's move on to the next page. Let X and Y be vector spaces over the field K, excuse me. Then X and Y are isomorphic if there is a linear map mapping X to Y such that F is a bijection. Okay, so that's what we saw in the previous result. That map is reversible, and it was actually a bijection, meaning injective, or one-to-one, and surjective, or onto, meaning that every element came from somewhere. Every element in the codomain came from somewhere in the domain. So in other words, is the map reversible? If it is, then we say it's a bijection. Okay, now to show injectivity, if f of x is equal to f of y, we must show that x equals y. And surjectivity, for all elements of the codomain, there exists an element of the domain x such that y is equal to f of x. Okay, Theorem 38. Let x be the set of all polynomials of the form ax plus b, where a and b are real numbers. Then there's a vector space isomorphism from x to 2 space given by f of ax plus b is the vector ab. Okay, so we need to show that that this map is a linear map, and then we need to show that it's both injective and surjective. So first, f of a1x plus b1 plus a2x plus b2 is equal to f of a1 plus a2 times x plus b1 plus b2, and this maps to a1 plus a2, comma, b1 plus b2. Okay, now f of a1x plus b1 plus f of a2x plus b2 is a1 b1 and then plus a2 b2, which is the same as we have here. Okay, so now let's check the scalar multiplication property. F of k times ax plus b is f of kax plus kb, which is ka comma kb. We can factor the k out of this, and then ab is f of ax plus b. Okay, so we see it has the second property, the additive property. It has the scalar multiplication property. So f is a linear map. Okay, so now that we know it's a linear map, let's check that f is injective. So to show that F is injective, suppose that f of a1x plus b1 is equal to f of a2x plus b2, well then that says a1 b1 equals, because this is a1 b1, this is a2 b2, okay, and straight away that satisfies the definition of one-to-one or injective. So F is one-to-one, or we could say injective. Now F is also surjective, since if I take AB in the codomain R2, is there an element in the domain that maps to that? And the answer is yes. So f of ax plus b equals ab. So every element came from somewhere in the domain. Okay, so f is injective and surjective, so f is bijective. Bijective. And it is a linear map. A bijective linear map is a vector space isomorphism. All right, Theorem 39. Let C be the complex numbers. This is R adjoin I. Be the vector space of complex numbers AI plus B over the field R. There's a vector space isomorphism. So let's have a look. Now this follows immediately from the previous result. So we see as vector spaces, these have the same algebraic structure. There's a vector space isomorphism. But there's more. So let's have a look at the more. Okay, so suppose we have a0 plus a1 I plus a2 I squared, and so on, up to an I to the power of n. Now, since I squared is minus 1, what this is a0 minus a2, I to the power of 4 is 1, plus a4 minus a6, and so on, plus a1 minus a3, because I to the power of 3 is minus I, plus a5, and so on, all times I. So this is a complex number. Okay, now, so we have f of ai plus b is ab, but we can do something similar with the product. So let's expand the inside of this. Now I squared is -1, so that's a minus. Then we have a2b1 plus a1 b2 all times I, and then b1 times b2. Okay, so this, we can apply the map to this. And so what we get then is a1 b2 plus a2 b1 comma b1 b2 minus a1 a2. So we can also define this on the product, all right, which is kind of interesting. All right, let's move on to the next page. Fundamental subspaces, rank, and nullity. Let X and Y be vector spaces over the field K. Let F map X to Y be a linear map. If the span of x1, x2 up to xn is equal to x, then the span of f of x1, f of x2, dot, 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 up to f of xn is equal to f of x. Okay, so let's have a little look at this. Span of f of x1, f of x2, up to f of xn equals the set of all linear combinations of these. So alpha 1, f of x1, alpha 2, f of x2, alpha n, f of xn. Okay. Now, since we have a linear map, we can express this pulling the f out. Since f is a linear map, okay, so is equal to f of span of the vectors x1, x2, etc. up to xn, which is f square bracket x. Okay, kernel and image. Let f map x to y be a linear map. Then the kernel of the map f is given by, it is the set of all vectors x in the domain x such that f of x is the 0 vector. So it's the set of all vectors that get mapped to the 0 vector. Theorem 41, if f of x is a times x for some matrix A, then the kernel of f is the null space of A. Hence, the kernel of f is a subspace of x. Okay, so the kernel f subscript A equal to the set of all x in the vector space x such that a x is the 0 vector. Now if you have a look at this, this is the definition of the null space of A. And since the null space of A is a vector space, so is the kernel. And hence kernel is a subspace of X by definition of a subspace. Because the definition of subspace says that it has to be a subset that is also a vector space in its own right. Okay, image of F. This is the set of all X in vectors X in uppercase X such that there exists a vector Y in uppercase Y satisfying f of X is equal to Y. So remember back when we talked about the map sending the integers to the real numbers by squaring that integer, and the image of the map was the set of all squares of integers, so 0, 1, 4, 9, 16, 25, and so on. So this looks a little bit tricky, but it's actually not so difficult to conceptualize what the image is. It's the set of all outputs of your linear map. Okay, theorem 42. If f of x equals ax for some matrix A, then the image of f is the column space of A. And remember, that's the set of all linear combinations of the columns of the matrix A. Hence, the image of f is a subspace of Y, because the column space is a vector space. Okay, next page. Definition 35. The rank of a linear map F is the dimension of the image of F. The nullity of F is the dimension of the kernel of F. If f of x is equal to A times x for some matrix A, then the nullity is equal to the dimension of the null space, and the rank is the dimension of the column space, also equal to the dimension of the row space of A. Because the row space and the column space have the same dimension. Theorem 43. Let x and y be finite dimensional vector spaces over K with dimension n, and let F mapping x to y be a linear map. Then the rank of F plus the nullity of F is the dimension of x. In other words, the sum of the dimensions of the kernel and the image of F is equal to the dimension of x. Example 11.8. Okay, we have a 3x3 matrix here with integer entries. The map FA from real numbers to real numbers given by FA of x equals A times x is a linear map. So we've seen this earlier. Find a basis for each of the null space and the column space of A. Calculate the rank and the nullity of the matrix A and verify that they add to 3. Okay, so what we want to do here is row reduce this matrix. So we've got A equal to 2 minus 1, 3, 4 minus 2, 6, minus 6, 3, and minus 9. Okay, so what we want to do here is multiply the first row by 2. And then we will replace row 2 with row 2 minus row 1. You can see they're identical. And now let's multiply row 1 by 3 over 2. So let's see, we'll get 6. We'll get minus 3. and we'll get 9. Okay, then we still have -6, 3, and -9. Okay, now we can see that row 1 and row 3 added together will give us a row of zeros. So we have 2 rows of zeros. And then now let's multiply row 1 by 1/3. So we'll get back this original row 1. Okay, there we go. So this is not quite in row reduced echelon form. If we just multiply through by a half, then we have row reduced echelon form. But this shows us, all right, so let's actually just write the row reduced echelon form. So we have 1 minus a half and then 3/2. So this is in row reduced echelon form. All right, so now for the column space. So what we want to do is identify, we've got one pivot and it appears in the first column, and so we extract the first column of the matrix A. So the image of F is the column space of A, which is spanned by the first column of A. Two, 4, -6. Okay, so, and we can even see that all of these are divisible by 2, so let's divide that throughout by 2. So 1, 2, -3 is a basis for the image of the map F. Okay, so let's just check. Take an arbitrary element of the image. Okay, just to check. Randomly choose (3, 1, -4, for example. All right, and then let's just map. So F of 3, 1, -4 is equal to the matrix times that vector. Okay, so what do we have? 6 -1 is 5 -12. That's -7. And then second row times this column, we have 12 -2 is 10, plus 6 is 16. Hope I got this right. No. Okay, so 6 times 4 is 12, -2 is 10, and then -24. 10 -24 is -14. Okay, last row times this column, -18 plus 3 is -15, then plus 36. 36 minus 15. Have I got that right? -18 plus 3 is -15. Okay, 36 minus 15 is 21, isn't it? Yeah. Okay, there we go. So we get this. So this is clearly an output of F, clearly in the image of F. But note it's also in span of 1, 2, minus 3. In other words, it's minus 7 times 1, 2, minus 3. Okay, so now for the kernel, and so we can just look at the row-reduced echelon form for the kernel. So if a times x, y, z is the 0 vector, then it's the case for the row-reduced echelon form times x, y, z also. But we'll take 2 minus 1, 3, which will be easier to deal with than those fractions. So we have this, all right? Now what we want to do is expand this out, and so we will get 2x minus y plus 3z equals 0. I'll need to grab some more paper here. Okay, and so I want to solve this for x. So I have x is equal to a half y minus 3 over 2 z. Now I can add on y equals y because it's true. But I can write this as 1y plus 0z. And z is equal to z, or 0y plus 1z. Alright, so now let's write our element of the null space, xyz, is 1/2, 1, 0 times y plus minus 3 over 2, 0, 1 times z. And so I have a linear combination of these two vectors. Whenever I have an element of the null space, I can express it as a linear combination of these two. So what we learn then is that the null space of A, which is the kernel of F, is spanned by these two vectors. Okay, and so this is a basis for the kernel of F. All right, now let's consider the dimensions. So this is the nullity of F is the dimension of the kernel of F. And so in this case it's 2. Now the rank of F is the dimension of the column space, or the image of F. And so that was equal to 1 because we had one vector there. Okay, and so now we should just note that rank plus nullity is 1 plus 2, which is 3, which is the dimension of the domain R3. Okay, let's move on to the next page. Okay, let F map 4 space to 3 space be a linear map given by this. Find a basis and dimension of the image, find a basis and dimension of the kernel. So we have F, I'll write this vertically, is equal to 1 minus 1, 1, 1, 2 minus 2, 3, 4, 3 minus 3, 4, 5, times x, y, z, t. Okay, well, not quite. I mean, we would have to transpose all of this for this to be true, but it's easier to work with it this way. So what we want to do is row reduce this matrix here. Okay, so we multiply row 1 by 2. Now we replace row 2 with row 2 minus row 1. And now we divide, or sorry, we multiply row 1 by 3 over 2. In preparation for taking a difference between that and row 3. Okay, so let's take replacing row 3 with row 3 minus row 1. So 0, 0, 1, 2. And we'll replace row 1 with 1/3 of row 1. All right, now we can see that row 1 and row 2 are identical, so we can replace row 2 and row 3 are identical, so we can replace row 3 with the difference and get a row of zeros. Now we want to replace row 1 with row 1 minus row 2. Okay, so now we have the row reduced echelon form of the matrix A. Okay, let's identify where our pivots are. Here and here. So the pivots are in rows 1 and 3. So we extract columns 1 and 3 of A to form basis for the column space of A, which is, remember, the image of the map, F. Okay, so let's just say 1, 2, 3, 1, 3, 4 is a basis for the image of F and has dimension equal to 2. So we know straight away from the rank plus nullity theorem that the dimension of the kernel has to be 2. All right, so let's now deal with the kernel. So for the kernel of F, I guess that's uppercase F. Likewise here as well. If we have A times x, y, z, t equal to 0, 0, 0, then it's the case for the row reduced echelon form too. And so now expanding this out, we have x minus y minus t equals 0 from the top row. And then we have z plus 2t equals 0. And so from this, let's turn to the next page where there's some space. We want to solve this for x and for z. So x is equal to y plus t, y is equal to y, z is equal to minus 2t, and t is equal to t. Okay, so let's write x, y, z, and t is equal to 1, 1, 0, 0 times y plus 1, 0 minus 2, 1 times t. So we get a basis for the kernel. 1, 1, 0, 0, 1, 0 minus 2, 1 is a basis for the kernel of uppercase F. And notice nullity is 2 as expected. 2 plus 2 is 4. Okay, next page. Let F map x to y be a linear map with f subscript a of x equals ax for some square matrix A. F is injective or one-to-one if and only if the determinant of A is not equal to 0. If and only if the null space of A is equal to 0, trivial, meaning the kernel of F is trivial. Okay, so if f subscript a of x equals ax, now first suppose the null space of A is trivial. Assume f subscript a of x equals f subscript a of y. Then we have ax equals ay, so a outside of x minus y is the 0 vector. Since null space of A is trivial, the only possibility then is, so we must have x minus y is the 0 vector, so x is equal to y, which shows you that f subscript a is injective or one-to-one. Conversely, suppose fa is injective and x and y are not equal, nor are they equal to the 0 vector. Okay, we then have ax equals the 0 vector equals a y, which is a contradiction.